Recall from college algebra that if f of x is an elementary function, then the graph of y equal to f of x plus or minus a constant resembles the graph of the parent function. It's just shifted horizontally to the left or to the right by c units. In trigonometry, we call that a phase shift. Definition: the phase shift of the graph of y equals sine of x minus c or cosine of x minus c is equal to c. So let's practice graphing a sine wave that has a phase shift. Now, anytime we graph a sine wave, we're definitely going to need to include the 5 key points on at least one fundamental cycle of the graph. So we're going to graph y equals sine of x minus pi over 4. Now, observe that the parent function for the graph we're considering is the graph y equals sine of x. Sine of x completes one fundamental cycle over the interval from 0 to 2 pi. So as the argument x ranges between 0 and 2 pi, the sine wave hits all 5 key points in that roller coaster shape. The new graph that we're going to consider is going to hit all 5 key points, but it's going to be shifted to the right by pi over 4 units. So we can see here that the phase shift is pi over 4 units. Now, positive pi over 4 means that the shift is to the right. Now, you're thinking, wait a minute, it's minus pi over 4 in the example. But remember, with a horizontal transformation from college algebra, the sign inside the argument is opposite of the direction that it shifts horizontally. So when we have a minus c inside of the argument of our trig function, it shifts c units to the right. If we have a plus c inside the argument, it's going to shift c units to the left. So the final result of our graph should be a sine wave shifted to the right by pi over 4 units. Now notice, because there's no new coefficient here, that the amplitude is going to be just 1. The period of this shifted sine wave is going to be the same as the period as the original function. So just as this argument, an original sine wave, ranged between 0 and 2 pi, then we can say that the argument of this new sine wave is also going to range between 0 and 2 pi. But when we solve for x, of course, by adding pi over 4 to all 3 parts of that inequality, we can see now that the fundamental cycle of our shifted sine wave is going to be from pi over 4 to 2 pi plus pi over 4. Let's go ahead and do a little side work and execute this arithmetic here. If we want to add 2 pi over 1 to pi over 4, we would need a common denominator of 4. So we can think of this as 8 pi over 4 plus pi over 4, or 9 pi over 4. So the fundamental cycle for our shifted sine wave is going to range from 9 pi over 4 to 9 pi over 4. Looking at the scale already labeled on the graph, we have the quadrantal stops labeled. Well, halfway between 0 and pi over 2, we have pi over 4. So we can see that the scale for a single tick mark on the x-axis is pi over 4. So if I count in multiples of pi over 4, I can label the entire scale. So there's 1 pi over 4, 2 pi over 4, which reduces to pi over 2. This would be 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and then 7 pi over 4. We're going to end at 2 pi, and it looks like we're going to need one more mark. I'm just going to add it here on the end, 9 pi over 4. So the sine wave that we're going to graph is going to start at pi over 4 and end at 9 pi over 4. Remember, sine begins and ends on the x-axis. So there's the beginning and the end of the fundamental cycle. Now, the sine wave also crosses the x-axis at the midpoint between those two values. So let's calculate the midpoint between pi over 4 and 9 pi over 4. Recall that to find a midpoint, you add the two endpoints and then divide by 2. So I'm going to add the two endpoints and divide by 2, or I'm going to think of it as multiplying by a half. So we're going to have 1/2 times 10 pi over 4. If we cancel the 2 into the 10, it looks like the midpoint will occur at 5 pi over 4. So at 5 pi over 4, the sine wave is going to again cross the x-axis. Now notice this distance is equal to this distance, and I can verify that just by looking at the graph. Also recall in our 5 key points that halfway between the first two x-intercepts, we obtain the maximum value. So I need to find the midpoint between these two values, and that will determine the x-coordinate for the maximum. So let's find the midpoint between those two values. So I'm going to take pi over 4 and add it to 5 pi over 4 and divide by 2 to get the midpoint. So we need to evaluate 1/2 of 6 pi over 4. Reducing our fraction here, it looks like the maximum value is going to occur at 3 pi over 4. Now, as we've been doing, I'm going to use 2 tick marks on the y-axis to represent 1 unit so that I can see the graph clearly. So the maximum point for this particular sine wave is going to occur at 3 pi over 4 and 1. And I'm going to go ahead and label that for good measure. The last point that we need to locate on our sine wave is where the minimum point occurs. Recall that the minimum point occurs halfway between the last two x-intercepts. So I need to find the midpoint between 5 pi over 4 and 9 pi over 4. So I'm going to find 1/2 the sum of 5 pi over 4 and 9 pi over 4. So it looks like we need to evaluate 1/2 times 14 pi over 4, and we can reduce here to obtain 7 pi over 4. So when x is 7 pi over 4, the y value hits the minimum of -1. Then you can see the roller coaster shape. We have one fundamental cycle of sine, and it has been shifted to the right by pi over 4 units. Please keep in mind that we're only graphing one cycle of the sine wave, but this picture repeats across the entire domain. So the entire domain of this function is -infinity to infinity. The range has not changed because we did not have an amplitude change. It still ranges between -1 and 1. And to be complete here, let me go ahead and label my minimum point, 7 pi over 4 and -1. Now let's use our graphing calculator to examine the relationship between our original sine wave and the new sine wave that we're considering, which is sine of x minus pi over 4. Recall that when you're graphing a trig function, it's convenient to use your zoom function, option number 7, zoom trig, to see a clear picture of the graph. Notice the blue curve here is the original sine wave. The red curve is the sine wave that has been shifted to the right by pi over 4 units. Now remember, in zoom trig, each tick mark on the x-axis represents pi over 4 units. So halfway between those two units, we've got pi over 4. Or if you want to see it a little more clearly, you can manually change your window. Let's change the x scale from its current value, 1.57 is approximately pi over 2. Let's change that to a scale of pi over 4. Going to give us a few more tick marks on the x-axis, but then we can observe that the red curve has its initial x-intercept at pi over 4 exactly. Anytime you graph a trig function, it's important to have your axes labeled, and for sine and cosine, you identify all 5 key points. In addition to a horizontal transformation, you learned vertical transformations in college algebra. We can execute that on the graph of a sinusoid as well. No fancy name here, it's just called a vertical shift. The vertical shift of the graph of sine of x plus d or cosine of x plus d is d. So the difference between a phase shift and a vertical shift is the placement of that constant. Notice here the constant is outside the function. That indicates a vertical shift. When the constant is inside the argument, added or subtracted, then we've got a phase shift. So let's graph one cycle of y equals cosine of x plus pi over 3 plus 1. Notice we have a constant added inside the argument and a constant added to the entire function. So beginning with the amplitude, because the coefficient here is 1, the amplitude has not been altered from its original state. The amplitude is 1. Because we're adding pi over 3 inside the argument, this is a phase shift, so I'm going to record this as negative pi over 3. Or you can state it as pi over 3 to the left. Now also we have a constant outside the cosine function. This indicates we have a vertical shift, so we're going to move the graph of this function up 1 unit. Now that's going to give us a new center for our graph. So as I've been doing, I'm going to use a scale of 2 tick marks for 1 unit on the y-axis, and then I'm going to take this vertical shift and use that to imagine a new horizontal axis for the cosine wave. Because the amplitude is 1, our cosine wave is going to stretch up 1 unit above this center line and 1 unit below the center line. So we should see the entire bowl shape within those 2 boundaries. Now let's determine the 5 key points for this cosine wave. Recall that for the parent function y equals cosine of x, 1 fundamental cycle occurs for x ranging between 0 and 2 pi. For our new transformed function, which has a horizontal shift, x plus pi over 3, 1 fundamental cycle is going to occur for the argument x plus pi over 3 between 0 and 2 pi. If we solve for x in the middle of this inequality statement, we can simply subtract pi over 3 from all 3 parts. We'd end up with negative pi over 3 less than or equal to x less than or equal to. Now we need to execute 2 pi minus pi over 3. So I'm just going to do a little side work down here. A common denominator would be 3. So we need to evaluate 6 pi over 3 minus 5 pi over 3. And that's going to give us an upper value of 5 pi over 3. This means that this shifted graph is going to have the first point of its fundamental cycle at x equals negative pi over 3, and the last point, which is a maximum, at 5 pi over 3. Now, if we look at the scale on our x-axis, we have multiples of pi over 2, and then halfway in between those labeled tick marks, we have pi over 4. So in order to locate negative pi over 3 and 5 pi over 3, I'm going to add some information to the graph. Now remember, it might be easier to think about this in degrees. This is negative 90 degrees, and I need to label negative pi over 3 or negative 60 degrees. So what I'm going to do is divide this in thirds. This will be negative pi over 6, and then 30 degrees later we have negative pi over 3. So each of those tick marks, excluding the one in the middle, this would be a pi over 4 stop. Each of those tick marks will be 30 degrees apart. So I'm going to go ahead and do that on this side as well. We have pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, and 5 pi over 3. I'm going to stop there because that's where our graph is going to stop. So at the beginning of our cosine wave and the end of our cosine wave, if we think about our parent function, the graph is going to reach its maximum. So looking at x equals negative pi over 3, the graph is going to reach its maximum, which is 1 unit above that center line. And at the end of the graph, at x equals 5 pi over 3, the graph is also going to reach its maximum. So labeling our 5 key points here, this is 5 pi over 3 and 2. This is negative pi over 3 and 2. Now, halfway between the 2 maximums in cosine, we have a minimum point. So to locate the minimum point for this shifted graph, we need to find the midpoint between negative pi over 3 and 5 pi over 3. To find the midpoint, we're going to add those values together. negative pi over 3 and 5 pi over 3, and then divide that sum by 2. We can think of that as multiplying by a half. So we need to evaluate 1/2 times 4 pi over 3. Reducing, we're going to end up with 2 pi over 3. So on our graph, when x equals 2 pi over 3, cosine is going to hit its minimum. Its minimum is going to be 1 unit below that horizontal center line. So this would be ordered pair 2 pi over 3, 0. Now, keeping our eyes on our original parent function, remember that halfway between the maximum and minimum, cosine is going to have an x-intercept. In this case, halfway between the maximum and the minimum, cosine is going to cross this center line. To figure out where that occurs, we need the midpoint between the x values of the maximum and minimum. So we're going to have half the distance between negative pi over 3, or the midpoint between x equals negative pi over 3 and 2 pi over 3. This gives us 1/2 times pi over 3, or pi over 6. So when x equals pi over 6, where cosine originally had an x-intercept, this new cosine is going to cross that center line. And for the last of our 5 key points, we know that the original cosine wave crosses the x-axis halfway between its minimum and maximum. So we know that halfway between its minimum and maximum, this cosine wave is going to cross that center line. So we need to find the midpoint. So we're going to take 1/2 of the beginning 2 pi over 3 and the end 5 pi over 3. That's going to give us 1/2 of 7 pi over 3, or 7 pi over 6. So when x equals 7 pi over 6, our cosine wave is going to cross that center line. Let me be careful to label. This is 7 pi over 6, 1. And for good measure, this one over here was pi over 6, 1. Now we can construct the bowl shape indicative of cosine, and we have graphed one fundamental cycle of cosine. Now, if we think about the 5 key points of our original cosine wave, notice the one that we've graphed has been shifted in a couple of ways. So here is, I'm just going to sketch it in, the 5 key points that belong to our parent function. The graph that we've done in green has been shifted to the left by pi over 3 units and up by 1 unit. So we still have the same snapshot, it's just in a new location. Even though we've only graphed one fundamental cycle, we know that this shape is going to repeat across its entire domain because cosine is periodic. The entire domain is, in fact, negative infinity to infinity. So don't forget, this graph does extend beyond the snapshot that we have sketched here. Now, because the amplitude is 1 and we've experienced a vertical shift, the range changes. The minimum y value is 1 and the maximum y value is 2. Let's finish with one more example. Working backwards here, we're going to start with a graph and see if we can identify the equation of the graph. In example 6, it says, write the equation of the sine wave shown below. Notice the instructions indicate that this is a sine wave. Since we are going to write this in terms of sine, we need to identify one fundamental cycle of the sine wave. Remember, sine looks like a roller coaster shape. So I'm going to consider the beginning of the sine wave to be at this point right here, and then I can see one fundamental cycle of the sine wave across this interval. So to write the equation of this, let's recognize first of all the amplitude. Remember, the amplitude is half the distance between the maximum and minimum values. This handy little dashed line right here identifies the center. So the amplitude looks like a distance of 2. So 2 units above the center, 2 units below the center, we can recognize the amplitude. Also notice, because the sine wave is oriented like the original sine wave, it has not been reflected across the x-axis, so we don't need to introduce a negative here. Now, we need to check to see if there is either a phase shift or a vertical shift. Remembering that the original sine wave starts at 0, we can observe that this one has been shifted to the right by pi over 2 units. So the argument is going to be x minus pi over 2. Also observe that the new center line here has been shifted up 1 unit. That indicates a vertical shift of 1. So it's very important that we know the 5 key points for both the sine wave and the cosine wave, that we can recognize a change in amplitude, a change in phase shift, or a vertical shift.